Welcome to week 2, lecture 2 of Science of the Sea, where we are going to talk about continental drift and plate tectonics. We've introduced the ideas a little bit already, but we'll get more into the details of it now. So the continents move. We've discussed that already. They move slowly but constantly. And the idea, people started thinking this more than 100 years ago now, from a hypothesis that was not very well accepted to now it is a unifying theory. And a theory, for those of you who don't know, a theory within science is something that essentially has so much evidence behind it that if it were to ever be found to be untrue, it would change everything in the entire world because so much depends on it. So that's what a unifying theory is. It unifies so many things together and is now so important, and there's so much evidence behind it that it's almost impossible to not feel we know that it exists. It is there for a reason. A hypothesis is an educated guess, something we think might be true. And it takes a hypothesis being proven and supported for years and years and years in order to become a theory. So a lot of times in casual talk, we say, oh, that's just a theory. But what we should say is, oh, that's just a hypothesis. By the time something is a theory, then there's a lot of evidence behind it and it's very well accepted. So we should change our general thinking and way that we talk about theories. But theories are super important to science. I'll get off my soapbox on that now. So Wegener and his continental drift theory. Alfred Wegener, around 1912, proposed that the continents drift. He saw a lot of evidences that we'll go through, from fossils, climate patterns, rocks, glaciers, and it was an idea that was rejected at the time because nobody could see a way, in the early 1900s, nobody could see a way for this to happen. How could entire continents push through solid rock? That doesn't make any sense at the time. We did not understand what the earth and the core were made of. We didn't understand all the mechanisms that we do now. The fun part of this is that Alfred Wegener wasn't even a geologist. He was a meteorologist, but he, saw an issue and he proposed a theory for it, a hypothesis at the time. And we're going to look at some of the evidence for that. So the first thing that he started to notice is that Africa and South America have such a similar shape that they could have fit together at one point in time. And that was kind of where this all began from. This is an image of Pangaea, the time millions of years ago when the Earth was a supercontinent. So Pangaea is the name of that supercontinent, and over millions of years, the continents have spread apart and become the 7 continents we have today. So some of the evidence that Wegener looked at were fossil evidences across continents. We're going to look at an image of that here in a minute. Matching rock types and mountain ranges. So he found rock deposits that were similar on different continents. So how could that happen, right? And same thing with glacial striations. He saw evidence of glaciers that looked like they had moved in a certain direction, and they didn't match up with how the continents are today, but they would have matched up had we looked at, the Pangaea model here. So those were some of the things he looked at. Here's the fossil evidence. This is an image that I really like. It shows just a few of the fossils that are found across continents. So this little guy, none of these are water animals, by the way, not ocean animals anyway. So this Signathus is an animal that its fossils were found both in South America and Africa, and it is not something that could have traveled across the ocean as it is today. So this is a freshwater Mesosaurus, and its fossils were also found in both South America and Africa. And then we have the Lystrosaurus. I always have a hard time saying that one. Lystrosaurus, whose fossils were found in India, Africa, Antarctica, quite a few places. And think about it, an animal like this probably isn't going to survive in Antarctica as it is today. But had it been in a different place, it obviously would have had a very different climate millions of years ago. The last one is a plant. This Glossopteris is found across all of the continents. And again, that's not something that could easily have traveled, especially long, long before humans. So those are just some of the fossil evidences that Wegener looked at. Again, he was not well accepted at the time, but as time went on, his theories became much more accepted because in the 50s and 60s, ocean exploration revealed a lot more than what we used to know. The seafloor isn't flat at all. We had big ocean ridges and underwater mountains that stretch for hundreds of miles. In the center of these ridges were deep valleys where magma was rising up from below. And in 1962, a scientist named Harry Hess was a geologist who proposed that the seafloor can spread, that new crust forms at ridges and old crust sinks at trenches. So again, I'll give you a little link that you can read more about Harry Hess if you want to. It's not going to be required, but just for fun if you're interested in that. But he essentially solved Wegener's problem of not having a mechanism for continental drift. The seafloor spreading is the mechanism that causes continental drift. And so now everything started to fit together into one unified theory. So now paleomagnetism, we're not going to get super into this, but it is another evidence of continental drift. So iron minerals in lava align with Earth's magnetic field. So the minerals within the lava essentially they become stripes along the ocean floor. We can see that the magnetism match up. So they mirror across ridges, that magnetism matches up, and over time, as Earth's magnetic field reversed, north became south and vice versa, we can now see those magnetic patterns on the ocean floor and see when and how the polarities reversed based on new crust forming at different times. So that's another evidence for continental drift. And again, you don't have to know a whole lot about paleomagnetism. You certainly don't need to know exactly how it works. What I want you to know is that it is an evidence for continental drift. So the unifying theory of plate tectonics. So here's where it all kind of comes together. So all of this evidence and understanding leads us to that our world is made up of different plates that float around on the asthenosphere, and then how they move is essentially plate tectonics. So all the interactions at boundaries are what make volcanoes and earthquakes and mountains and ocean basins and all the different things. And we're going to look at how those plates move next. So again, this is a picture you've seen before, but we have the lithosphere, which is the solid part of the mantle, and the crust that float around on the asthenosphere, and different plates have boundaries at different areas. This is essentially a plate boundary here where this oceanic crust is subducting or going underneath this continental crust. And that's a convergent boundary right there. And we'll talk about those in just a second. So the Pacific plate and the Hawaiian hotspot is another fun topic that we've already talked about a little bit. But here in Hawaii, the island sits on essentially the middle of the Pacific plate. So it's not at the edge of a plate. It's not at a boundary. And that plate is moving about 7 to 10 centimeters per year to the northwest. So Hawaii is actually underneath of a hotspot. A hotspot is a fixed plume from deep, deep in the center of the earth, essentially keep rising up from in that same spot. So that hotspot never moves. It's coming from the center of the earth. But the crust on top of it does move. So the Hawaiian Emperor Seamount chain, we're going to look at a map of that in just a second, essentially records millions of years of motion of, just a few centimeters per year for millions of years. So we can look at here, the red triangle is where the Big Island is now, where the active volcanoes are. And you can look at these ridges over time. These are other Hawaiian islands. Obviously, this is really zoomed out and you can't see the islands and it's underwater. But these are the Hawaiian ridges, and the Emperor's seamounts show that once upon a time, this area was here. So over millions of years, this is moving. And it's, an interesting theory and concept. And it can be a little bit hard to imagine since we don't actually feel and see that happening all the time. But if the Big Island is currently over the hot spot, what is the next island that will form? So one day there will be a new island, it'll be here, we'll move this way, but it'll be forming this direction. So plate boundaries and ocean features. So we're going to get much, much more into all the plate boundaries in the next lecture, but I just want to introduce them to you quickly now. Divergent plate boundaries are when two plates are moving apart, and a lot of times that'll form a ridge because new crust will form up through the hole left between those two plates. Convergent boundaries are when two plates come together, two plates crash together. That can cause trenches, volcanic arcs. The Mariana Trench is one of these examples. We'll get sometimes earthquakes when that happens. Transform faults are when two plates slide past each other. They slide past each other and cause a fault, like the San Andreas fault. Earthquakes a lot of times happen on transform boundaries as well. And again, Hawaii is interesting because it's not on a boundary. It's above a hotspot. So here is a different image of these plates moving and the boundaries. So transform boundary, when plates slide past each other. Divergent boundary, when two plates pull apart. And convergent boundary, when they push together. Here we see a trench forming because this oceanic crust is subducting underneath the continental crust because this oceanic crust is more dense. So the denser crust is always going to go below the less dense crust. When two ocean plates come together, we get a ridge when two ocean plates pull apart in a divergent boundary, we get a ridge because that hot molten asthenosphere comes up and bubbles up and makes a ridge. Here we have a volcano forming where one plate is subducting under another. Again, these are both oceanic plates, so there they might fight for a bit before one flows under the other. But again, the more dense plate will always subduct under the less dense plate. Okay, so that's enough of that for the moment. Like I said, we'll talk about it a whole lot more in our next lecture. And today we talked about Wegener's idea and how that led to the theory of seafloor spreading, which eventually led to the unifying theory of plate tectonics. Continents and oceans move as part of a dynamic system. We've been over that quite a bit now. The Earth isn't static. It's alive and constantly moving around. And the evidence of that is everywhere, even under our own island. So next time, we will be getting more into the plate boundaries, the seafloor features that each one causes, just a little bit more in depth than what we've been talking about right now. So I will see you in lecture 3.